Good morning, students. Our subject is Design of Concrete Structure 1. Our today's topic is Design of Staircase by Working Stress Method. In last part 2 and part 3, we solved numerical of dogleg staircase. In today's lecture, we are going to study about design of staircase. Next type, that is a open well staircase. Type 2, design of a open well staircase. Okay. Example number 1, a stair which open well is having a step of size. Here the step of size is given 280 into 150. 280 into 150 means the tread is given 280 mm and rise is given, it is given for one step having a step of size. This step of size is given. The arrangement of stair is as shown in figure. In figure, all the arrangement regarding staircase is given. Design of stair for a live load of 3 kilonewton meter square. The live load for the staircase is 3 kilonewton per meter square, and use M20 concrete mix. The grade of concrete is M20 and the grade of steel is Fe415. Sketch the details reinforcement. After designing the staircase, after that draw a sketch with detailed reinforcement. Okay, so here this type of staircase, it is called as a open well staircase. Here one 90-degree angle, 190-degree angle, and third angle is 90 degrees. So this staircase is a 270-degree angles. Okay, so here in 3/4 shape like this staircase is called as a open well staircase. Okay, so if hall size is narrow, or if arrangement is not possible like a dogleg staircase, at that condition you can provide a open well staircase. Okay, here arrangement of open well staircase is given here. A to B, here 10 steps are provided. 1 2 3 4 5 6 7 8 9 10. Here 10 between 1 to A to B, here 10 steps are provided. B to C, here 5 steps are provided. 12 13 14 15 16. And C to D, here C to D 27 18 to 27, these steps is provided. The this landing, the distance of the landing is 1400, means 1.4 meter. Here landing distance is 1.4 meter. Okay, so the steps here is 2800, means 2.8 meter. This to this distance is a 2.8 meter. Okay, so here also this landing is 1.4 meter and this step is 1.4 meter. Again this landing is 1.4 meter. The thickness of wall is 300 mm. Okay, this is all these arrangement of a staircase. So we have to calculate it: A to B loading, B to C loading, and C to D loading. A to B and C. So in this figure, all the arrangement of open well staircase is given here. The landing is 1.4 meter. The width of all staircase here is 2.8 meter. Here staircase width is 1.4 meter. And A to B span and C to D span, here loading is same, and B to C span, the loading is different. So we have to calculate here A to B loading load and B to C load here. Okay, so for first step we have to find here calculation of design constant. We have to find here a design constant. So before that, here M20 and Fe415 grade of concrete is given here. So for Fe415 and M20, for table number 21, sigma CBC, we have to find here permissible stresses in concrete. So permissible stresses in concrete, our grade of concrete is M20, so the bending stress is 7. So for sigma CBC, M20 is 7. And in table number 22, permissible stresses in steel reinforcement for M20 Fe415 is 230. Okay, so sigma CBC is 7 and sigma ST is 230 Newton per mm square. Okay, now first step we have to calculate here design constant. First constant is modular ratio M. We have to find here first constant modular ratio. To formula is 280 divided by 3 sigma CBC. 280 divided by 3 sigma CBC. It is a for M20 grade. The value of sigma CBC is 7. So 280 divided by 3 into 7 is 13.33. It is a value of modular ratio. Okay, now next we have to find here depth of factor, neutral axis depth of factor we have to find here. The formula to calculate K is M into sigma CBC, means modular ratio into permissible stresses in concrete divided by modular ratio into permissible stresses in concrete plus permissible stresses in steel reinforcement. So modular ratio is in first constant we find here modular ratio is 13.33. So 13.33 into 7 divided by 13.33 into 7 plus 230. This sigma ST for Fe415. The value is 230. So the K factor, the answer is 0.29. Okay, now lever arm factor we have to find here J. J is lever arm factor. So to calculate J, the formula is 1 minus K by 3. Formula is J is equals to 1 minus K by 3. Okay, so 1 minus K is 0.29. Here we find 0.29 divided by 3. The answer is 0.90. Okay, next we have to find here next design constant Q, that is moment resisting factor Q. We have to calculate here moment resisting factor. Okay, so Q is equals to 1 by 2 into sigma CBC into J into K. So 1 by 2 sigma CBC means permissible stresses in concrete is 7. So J is 0.90 and K is 0.29. J in third step we find here J is 0.90 and K is 0.29. So we find here the Q is 0.91. Okay. Now we have to find here effective span. Flight A, B and CD. Here the flight is A to B flight. Here A to B means 1.4 plus 2.8 plus 1.4 plus 300. So addition of these all 2.8 plus 1.4 plus 0.15 plus 0.15 plus it is equals to 4.5. Okay, so flight BC, AB is here and BC is here. So this length is 4.5 meter and this length is 1.4 plus 1.4 plus 1.4. Here you can see 1.4 plus 1.4 plus 1.4 plus these half 0.15 plus 0.15. So here 0.15 plus 0.15 total is 4.5. This distance is 4.5 meter. Okay, so effective span of AB is 4.5 meter. AB and CD, this D here, AB and CD it is the same 4.5 meter and BC span is 4.5 meter. It's also 4.5 meter. Okay, so now we have to calculate here load. We have to find here a load. This A to B we have to calculate here load on it. Okay, AB and BC we also have to calculate load on BC also, and AB and BC, AB and CD the load is same. C and D also load is same, only BC load is different. Okay, so thickness of waste slab. Thickness of waste slab, to calculate a thickness of waste slab the formula is L20 divided by L to L divided by 25. So L here we find here 4.5. So 4.5 divided by 20 to 4.5 divided by 25. So here thickness is 22 to 5 to 180. So this thickness between 180 to 225, 225, between these two we have to assume our depth. So we assume here d, capital D, 225, 225 we assume here, and the cover we assume here for staircase is 25. So to calculate small d is equals to capital D minus C. So capital D is 225 minus 25. So here 200. D, small d assume here 200. Okay, consider here 1 meter width of flight. Consider the flight of width is 1 meter. So live load is given here 3. In our numericals already in example live load is given 3. If floor finish is not given, then assume 1 kilonewton per meter. Okay, now we have to find here a weight of one step. You have to find here a weight. So weight of step, the formula is 1 by 2 into r into 25. Okay, so r means rise, 1 by 2 into rise is 0.150 meter. You have to take here meter into 25, so 1.88 kilonewton meter. Okay, so weight of one step is calculated. Now self weight of slab we have to find here. Formula to calculate self weight of slab is 25 into D into under root of r square plus t square divided by t. So this is a formula to calculate self weight. 25 into D, capital D is, we already find here capital D is 225 means 0.225. R is rise of the our step is 150 and trade is 280. So 25 into 0.225 into trade rise is 150 mm means 0.15 square plus 0.28 square divided by 0.28. It is a trade. So this load is 6.38 kilonewton meter means self weight is 6.38 kilonewton meter. So now we have to find here total load on going. Now we have to find here total load on going. So a total load on going and total load on landing both are different, because what's different here, from this distance is different and this weight is different, because here step is not here and here weight of step weight is included. So different between these ongoing, this it is called as a ongoing and this is called as a landing. So this weight of both is different. Okay, so total weight on going means it's also consider weight of step. So 3 is a live load, consider 3 is live load, 1 is floor finish load. Ongoing also consider weight of step, that is 1.88 plus weight of self weight, so 6.38. So the total of these ongoing load, total load ongoing is 12.26 kilonewton meter. Okay, 12.26 kilonewton meter. Now self weight of landing, we have to find here a landing. So to calculate a landing, formula is 25 into D. D is our depth, 225. So 25 into 225, that is 5.63 kilonewton meter. So self weight of landing is 5.63 and total load on going is 12.63. So total load on landing is self weight is 5.63 and live load also coming on it and floor finish load. So 3 plus 1 plus 5.63. So total load is 9.63 kilonewton meter. So the load on going is means the step load. Here steps load is 12.26 and here landing load is 9.63 kilonewton meter. Okay, So this diagram, flight of AB and CD both are same, so we calculate here one diagram, and flight of BC is different. So the span is is equals to 4.5 meter. So on steps the load is 12.26, and the landing load, here a landing load is 9.63. So landing load is 9.63, and step load is 12.26, and here also landing load is 9.63. Step of weight load is 12.26 and landing load is 9.63. Here landing load is 9.63 and ongoing load is 12.26. Okay, now we have to find here bending moment. We have to find here maximum bending moment. To calculate maximum bending moment, formula is WL square by 8. W we already find here, take which is a great. So from 12.26 and 9.63, 12.26 is more, so take 12.26. Length is 4.5 square divided by 8, so moment is 31.06 into 10 to the power 6 Newton mm. We calculated here moment. So now we have to check our depth is okay or not. Thickness of waste slab we consider here okay or not. So check by equating maximum bending moment and resisting moment. To check maximum and bending moment, so M is equals to QBD square. M is 13.03. Here we find moment is 13.03 into 10 to the power 6. Q is 0.90. Moment resisting design coefficient, it's a constant 0.90. So B is consider for 1 meter, so 1000 mm. D we have to find here. So 31.03 into 10 to the power 6 divided by here 0.90 into 1000, it is a T. So the answer is 184.66. Required 184.66, and we provided here D, we provided D, small d we provided here 2000. So sorry, 200. So 200, here we provided 200, so is greater than 184.66. So it's a safe, depth is safe. Okay, so now we have to find here main steel. Okay, so we have to find here a main steel for the steps and slabs. So AST, the formula AST is M in divided by sigma AST into J into D. Moment is 31.03 into 10 to the power 6. Sigma AST means permissible stresses in steel. For reinforcement is 230. So J is a lever arm factor. We already find in a step 1. So the value is 0.90. D is our depth is 200. So AST is 749.52 mm square. AST minimum we have to find here 0.12 percentage of AG. This is for Fe415. If Fe415 is given, for Fe415 this value is 0.12 percentage of AG. If Fe250 is given, then formula is 0.15 percentage of AG. AG means B into capital D. So 0.12, B is 1000 and capital D here, capital D is 2 to 5. Capital D here is 2 to 5. So take here percentage 0.12 divided by 100. So the answer is 270 mm square. From this 270 and 749, 749 is big value, so provide AST is 749.52 mm square. Assume diameter of bar is 10 mm. So consider here diameter of bar is 10 mm. Okay, now spacing S is 1000 into pi by 4 into D square divided by AST. So 1000 into pi value is 3.14 divided by 4 into 10 square. Here diameter of bar is 10. So 10 square into AST we provide here 749.52. So AST value is 749.52. So the answer is 104.79 mm. 104.79 mm. So first spacing is 104.79. Second, 3 into d is 200, so 3 into 200 is 600, and third criteria is 300. From these three, use whichever is less. First is 104.79, second is 600, and third is 300. So the least value is 104.79. So our diameter is provided 10 mm diameter. The diameter of our bar is 10 mm. Spacing is 100 mm as a main steel. Okay. So AST is 749, means area of steel is 749.52, and the diameter of the bar is 10 mm. Okay. So now we have to find here distribution steel. Take AST minimum for area of distribution steel. AST minimum is 270, so take a 270 mm and assume distribution steel bar is 8 mm. So the diameter of distribution steel bar is 8 mm. So spacing we have to find here 1000 into pi by 4 into d square divided by AST distribution. So 1000 into pi value is 3.14 into 4 into 8 square. Bar is 8 square. So ASTD means area of steel distribution is 270. So the value is 186.17. Okay. Second is criteria to calculate spacing is 5d. D is 200. So 5 into 200, the value is 1000 mm. And third, S is 450. So these, from these three, use whichever is less. From these three, 186.15 is less, so assume 180 mm. The diameter of our distribution bar is 8 mm and spacing is 180. So provide 8 mm diameter of bar about 180 mm center to center spacing as a distribution steel. Okay. Now next step is development length LD. So development length LD is equals to 280. This 280 is called as a sigma ST. Our sigma ST is 280, and 10 is our diameter of main bar. We consider here diameter of main bar is 10 mm. So diameter is 10. 4 into this value, it is a shear stress constant. So 0.8 into 1.6. So LD is 449.22. This value is called as a, this distance, it is called as a LD, and LD is 449.22, means 450. Assume here LD means development length. Here we provided development length. This is a cross. This is a cross sections of flight A to B and C to D. So rise is 150 mm, trade is 280 mm. It is called as a rise. This is a trade. Okay, so main steel here is 10 mm, about 100 mm center to center, and distribution steel is 8 mm, about 180 mm center to center. Okay, so this is a, it is a landing we provided here, and draw here diagram with reinforcement. Now flight BC. For flight BC, here also one cross section is given. LD, this development length is 450. Distribution steel same for both. At 8 mm bar of 180 mm center to center, and main steel 10 mm bar of 100 mm center to center. Rise is 155 and trade is 250, or consider same. Here step is less as compared to AB. The step is different. Up to this distance to landing is 1.44. Step distance is 1.44, and again landing is 1.44. The thickness of wall is 0.23 meter. Okay. So in today's lecture we solve example of open well staircase. So in open well staircase, what is different here? staircase angle is 270. So in 3 direction steps are provided. So we have to find the distance of A to load on A to B, B to C, C to D, all these we have to find here. And then AST, area of steel, main steel, area of distribution steel. After that spacing we have to find here, and give a check for a depth. Our depth is okay or not of the waste slab. Okay, so anybody having doubt in today's lecture, you can put your question in chat box. Okay, thank you.